Again, if you're in class, you can join the Zoom screen if you want to. You don't have to. Have reference table, sanitizer if you need over there when you enter. All right, let's get rolling here. Welcome back. Good morning. Hope you're doing well. Another rainy day. What are you going to do? Central New York, rain today, rain tomorrow. Hey, Thursday looks like some sun's going to pop out, so we'll enjoy the day, hopefully Thursday. I'm looking for a couple people. I'm looking for Michael, Micaiah, Kim, and Nidell. If you're here, please let me know. Please throw your name in the chat or unmute. Attendance gets a little bit more tricky when there's more people in person and back and forth. So again, thanks, Michael. I am looking for Micaiah, Kim, and Nidell. If you're here, please let me know. All right, let's check out the COVID report for today. Welcome back. COVID report for today, we have 356 active cases of COVID in the county. Resolved cases, we have 20,817 resolved cases in the county. So a lot of people had it, a lot of people overcame it. But with that, there was 419 deaths. So a few more people were added to the death toll from the weekend. Hospitalization numbers, there's 14 people in the hospital, 6 people in ICU. So that number increased. 6 people fighting for their lives from COVID complications. Vaccine numbers are increasing slowly. So those numbers, once we get to like 60, 70%, you'll see things really, really starting to open up. Cuomo said May 19th, things are really going to start to open up. Like the Stanley is going to have full capacity at the Stanley. It's been a long time since we've seen that, May 19th. Restaurants could have full capacity. All these things are going to really start to open up. But if we don't get this percentage up before then we could spread the virus quite a bit. It's called herd immunity. Once we get to a population of over 60, 70% of people that are vaccinated in the county, then the numbers of COVID cases would really start to decrease. It kind of mimic what's going on in July, August, September. It's going to take a while before we get to nothing. Hopefully we get to nothing. Hopefully we have no more cases. Hopefully this COVID virus just like dies out and doesn't affect people anymore. But once we get to 60, 70%, then that threshold will be decreased. Hopefully we get there sooner rather than later. Let's just check out the last piece of data of numbers that we have here. On May 1st, we have May 2nd there too. Let me move on over a little bit. May 2nd, last piece of data that we have here. Come on. We had 19 cases, 19 more cases on the 2nd. Nice, good data there. Day before that, there was 23. Day before that, there was 41. Day before that, there was 35 and 48. So for the most part, the last week's worth of data, we could see that trend is definitely decreased. Hopefully it does. My wife and I were talking about each day's numbers, and I was talking about with her, and it's just really tough to predict what's going on each week. We had a better idea, I don't know, around October, November of predicting, but now it's just very inconsistent. You can see increase, decrease, kind of looks like a sine curve or something. But it's really tough to figure out this trend. Hi, Micaiah. Please try to get here a few minutes earlier. Just a reminder, COVID's definitely in the area. Protect yourself, protect your loved ones, wear a mask, social distance. When we're in class, we will definitely social distance when we can. We are social distance up here too. So again, just a reminder, there is 6 people in class, and there's plenty of space for more people if you want to come back. My routine is very similar to what it is pre coming back to Proctor. You have a hard copy if you want to use a hard copy, and we'll do exit pass questions or examples more in person in that setting. All right, let's figure out what's going on for the best class of the day. So here we go. Welcome back. Quote of the week comes from an unknown source. Quote is, chemistry states, the more energy put into a bond, the harder it is to break. You put the energy into this bond, you put energy into this class, I'm going to know you're going to do well in this class. You're probably going to have a good bond with you. We'll have a good bond. It's hard to break that bond. Ask your classmates that took this class with me last year. Still say hi to them in the hallways. We have a good connection here. You have a bond with mom or grandma, whoever's at home, your aunt. The more energy you put into that bond with whoever's taking care of you or whoever's with you, maybe it's your brother, maybe it's your sister, it's going to be tough to break that bond. But chemistry states this as well. Nothing new. Chemistry states this quote, this fact. The more energy you put into the bond, the harder it is to break. Today is Tuesday, May 4th, 2021. May the 4th be with you. So day 1, Unit 9, we're going to continue on with acid, bases, and salts. We'll finish it up today and next class. We'll go through neutralization today. I'll start off with a demonstration. We'll watch a YouTube flick. We'll go through some guided notes. We'll analyze neutralization. And then we'll go through the examples together, and I'll give you time to work on the exit pass on your own. If we have time, we'll go through topic 5B, the last topic of titration. We'll watch a flick, notes, another flick, examples, and an exit pass. Maybe I'll do a demo tomorrow too. The attachments are below. The reference table is there. You have 3 videos you can watch over and over again if you need help understanding the topic as well. Does anybody have any questions before we begin today's class? Any questions at home? On routine back to proctor? Anything? Is it safe? From what I hear, the lunchroom's a little bit cray-cray, but there's a lot of people eating. I don't know. I haven't been down to the lunchroom. Lunchroom's a little bit congested, I guess. Boring. Nothing to do in the lunchroom besides eat. I haven't seen it. Some people are saying it's boring. Some people are saying it's a little chaotic. But yeah, there was a fight upstairs in the lunchroom. A classmate told me. But we don't fight. We're chemistry students. We know better than that. Any questions for me? Like ask your classmates that went through the routine. Maybe you're thinking about coming back. Maybe you're happy just sitting at home in your cozies. Do you? All right, here we go. Starting off with a demonstration, but before I do so, I do want to analyze what we talked about last class, which was indicators. So last class, we talked about acid-base indicators. Before we did that, we talked about the pH scale. So let's refresh again, the pH scale. What the heck is a pH scale? So I asked you what's a pH scale before we did this topic, and a lot of you guys didn't know too much about it. Now you should have more information to put in the pH scale. What do we know about the scale? We know the pH scale goes from 0 to 14. pH scale range goes from 0 to 14. We know that in the pH scale, there's a neutral point at 7. So 7 is going to be neutral. Oh, I messed those colors up. So let's try that again. 0 to 14. 0. We know 0 to 7 are going to be acids. We should know what makes an acid. An acid is going to have H plus ion, hydronium ion. We know there's strong acids. We know there's weak acids. The closer you are to neutral, it's going to be more of a weak acid. We know there's bases. Bases range from 7 to 14. What makes a base a base? Base is going to have hydroxide, OH negative. The more OH negatives you have, the more concentrated it is, it's going to be a stronger base. As the concentration of OH starts to get neutralized, it's going to be more like a weak base. We should know what makes an acid, what makes a base. What makes something neutral? It's going to be equal number of hydronium ions and equal number to hydronium and hydroxide. Hydronium, hydroxide are equal for neutralization. We should be aware of that. So we know the pH scale. In last class, we went through these little indicators. We talked about the indicator. We went through methyl orange. We talked about it. We talked about bromethymol blue, phenolphthalein, litmus, brome crescent green, and thymol blue. We know that there's a pH range for each indicator, and it's going to turn a different color. So these indicators are going to give you a quick little reference on the pH value. It's not going to tell you specifically what it is, but it's giving you a little heads up. Is it an acid? Is it a base? Today's demonstration, what I'm going to do, I'm going to take some methyl orange, and I'm going to take some phenolphthalein. I'm going to use those 2 indicators on top of one more. It's called a pH universal indicator. And we're going to predict what the pH value is of 4 unknown solutions. So we're using methyl orange, we're using phenolphthalein, and we're going to predict what the pH is going to be. So a demonstration for today, I have 4 unknown solutions. So demo for today, 4 unknown solutions. I think you can see this at home. So 4 unknown solutions, unknown number 1, unknown number 2, 3, and 4. So you check out those 4 unknown solutions, and you know that they're all clear. All clear. We're going to figure out what they're going to be. One of these is going to be water. One of them is ammonia. One of them is Sprite. And another one's going to be vinegar. Yeah, we really can't figure out what they are by just looking at them because they're all clear. Maybe you can predict, but they're all transparent, and we can't really tell what they're going to be. Yeah, you could smell them. You could waft them into your nasal passage. How do you waft? You bring this up to your nostril, and you bring the fumes up to your respiratory system. You don't want to huff this or get a direct hit of this because it could be something harmful for your respiratory system. So you don't want to put your nose right on top of this. You want to waft it into your, hey, whoa, I'm upside down there. Zoom out, it's way too close. Way too close there. I know it's upside down. Let's try this over here. Let's change up the screens again. So wafting it into your respiratory system. Probably wouldn't have a mask on. But if you're wafting it, you take this off. The Erlenmeyer flask would be away from you. You wouldn't bring it right to your nose. You'd bring the chemicals or the fumes up into your respiratory system. You're going to act like a little snob here. You're going to be try to breathe it in, smell what it might smell like. You don't want to directly inhale something you don't know what it is. You want to waft it up into your nose. That's the goal. But we're not going to waft them. We're going to figure out what these are by using pHs. So here we go. Again, a little bit more information here. Like unknown number 1, 2, 3, 4. They're all transparent, clear. We're going to figure out what these pHs are going to be. We're going to figure out what they're going to be over here as well. So again, what I'm going to do, I have these wells, and 1, 2, 3 wells that are vertical here. Unknown number 1 is going to be important to that well. This is going to be unknown number 2, and all 3 of those. Unknown number 3 is going to go here. Unknown number 4 would go here. So I'm going to pipette a sample of each into the wells. Once I'm done with that, I'm going to take the horizontal columns. This is going to be unknown number 1, 2, 3, 4. I'm going to take phenolphthalein. I'm going to place some drops into each one of these wells. They should turn in color. Same thing for methyl orange. And last but not least, I'll use a pH universal indicator. So here we go. Let's go through this experiment. I'm going to use these pipettes. They're dropper pipettes. There's a bulb on the top of it. If I press it and I put it into the solution, it's going to siphon up some of the liquid. So here we go. First one up, unknown number 1. Just going to squeeze a bulb. Oops. And then I'm going to put some of the sample in unknown number 1 wells. I am not going to contaminate. So these are like a one-time use. You use them one time, you like throw them out. Because if I use like a strong acid in here and then use a strong base in there, it's going to contaminate my solution. So it's a one-time use. This one's done. Next up, I have unknown number 2, doing the same exact process that I just did there. Taking a new pipette, squeezing the bulb. You can see some liquid coming up there. And I don't need a ton of liquid to figure out the pH levels. Unknown number 2, done. So nothing crazy going on here. Just me taking some clear liquid, probably looks like water to you, but it's not water, and transferring it to the wells. Unknown number 3, squeeze a pipette. You see it suctioning on up there. And some sample to the 3rd column. Looks a little bubbly, but it's clear. And last but not least, unknown number 4. New pipette. One other thing about these little pipettes for your future is there is one mark on these pipettes. There's one little grid line on these pipettes. Let's see if we can find that grid line. There's my pipette. Got my nails done for you guys too, so hope you like them. So we'll zoom on this pipette for a second. And there is one small grid line on this pipette. Can't really see it too well, but it's right there. There's a little mark there on this, and it's plastic. And that mark would represent 1 milliliter. 1 milliliter would be, I'm not sure if you can see it too well, but there is a little mark present there. Right there. And that would represent 1 milliliter. If you wanted 1 milliliter solution, you'd match it up to that point. You'd mark it up to that point and suck it up with a pipette. All right, again, here we go. We have unknowns in each one of these solutions. The first test we're going to be testing is phenolphthalein. This is phenolphthalein indicator. What I'm going to do with the phenolphthalein, I'm going to take a drop or two and put it in each one of these wells. Looks like I didn't clean that one up too well. Sorry, pink a little bit. So again, I'm taking the phenolphthalein. I'm going to drop it into each one of the wells, the unknown wells. If you check out phenolphthalein for a second, let me look at the reference table real quick. So reference table really quick, you check out phenolphthalein. Phenolphthalein is going to either turn colorless or pink. So colorless or pink. If we drop phenolphthalein in there, these chambers up here are going to be colorless or pink. If it's colorless, it's going to tell us the pH is going to be less than 8. 0 to 8, it's all it's going to tell us. It's an acid. If it turns pink, it's probably going to be a base. So 9, 10, 11, 12, 13, 14, it's going to turn pink. Let's see what happens here. So phenolphthalein indicator solution. It's a quick reference to tell if it is an acid or is it about the base. All right, phenolphthalein. Just a drop or two. Nothing. Oh, come on, look at that reaction. Drop or two, turning pink, definitely. Drop or two. Oof. Red, dark pink. And last one, no change in color at all. So that test right there, we figured out unknown number 1, 2, 3, and 4. Let's look at the indicators again. Let's predict what the pH might be. So hopefully you can see this image at home. We're again just focusing on phenolphthalein. I don't care about anything else but phenolphthalein. 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 All right, first test. First one we analyzed. I don't think I can draw my picture here. But anyways, it was clear. And we know that clear is going to have a pH 8 or less. So 8 or less. So it's going to be less than 8. Since it's less than 8, we should know it's probably going to be an acid. So on my sheet right now, I'm just going to write an acid on the bottom, just an A. It's probably going to be an acid. It's less than 8. Next one up, we have a light pink. So this is how it works out here. If it's colorless, it's less than 8. If it's a light pink, it's going to be closer to 9. If it's a darker pink, it's going to be higher up on the scale. So it is a light pink. Maybe you want to represent something like this. You don't have to. Light pink to maybe like a red. Light pink is going to be a pH close to 9. So that one, it's a lighter pink. pH 9 is going to be maybe a weak base. Next one up, we have a dark pink. That's going to be probably a stronger base. It's further away from colorless. It's a dark pink. So maybe a strong base. And last but not least, this is colorless. It's going to tell us that it's just going to be less than 8. It's probably going to be some sort of acid. That's all we can determine from the phenolphthalein test. We can figure out acid, weak base, strong base. Easy. That one's an easy test. Let's try out the methyl orange. Let's see what happens when we take some methyl orange. Figure out what happens in the scale. Methyl orange, again, is going to turn red, orange, or yellow. Red, orange, yellow. Let's see what happens here. Methyl orange indicator. So again, you saw that I have the 4 unknowns. Methyl orange, here we go. It's a drop or 2. Unknown number 1. Okay. 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 It's like we're doing Easter eggs, dyeing Easter eggs. Could swirl them up a little bit. Mix them all together, mix acid and bases. There's a poisonous gas in here. Well, if you mix a strong acid, strong base, it's going to give you a poisonous gas. You won't do that. Yeah? Maybe next time. Maybe next time with chemistry with Mr. Brown. Little glare. Probably not though. Not much I can do about this one over here. All right, so you can see the colors there. Methyl orange, the first one, looks like a light pink, looks like a yellow, more of a orangish yellow, and definitely an orange. Hopefully you can see this. If you're colorblind, you're gonna have a hard time seeing these, obviously. So let's check this out with the pH indicator. Predict the following. Here we go. The first one looks like it's a red. We are using methyl orange again for the test. Methyl orange. I don't care about anything else but methyl orange. Yeah, this would have been a lab that you would have performed in class, but with the situation, obviously, I'm doing it for you. You're figuring it out with me. So here we go. The first one looks like it's a red, and red on the pH scale, red. All we know it's going to be less than 3.1. We did this last time. Less than 3.1, it's probably going to be a strong acid. So I can say now it's going to be a stronger acid. Strong acid. We're pretty confident with that. We knew it was an acid for the phenolphthalein test, but now we know it's red. It's going to be a stronger acid. Next one's a yellow. Let's match that up. Yellow. What do we know about yellow? The pH is going to be greater than 4.4. So 4.4, we're going to have to know it's going to be yellow. It could be 4.4, it could be 14. It's greater than 4.4, so I'm going to leave weak base. It looks like it's a weak base. Next one kind of looks like it's a weak base or maybe a strong base here. Maybe go a little further. It looks like an orangish yellow. So yellow, orange is going to be in the middle. Orange color would be right there. Maybe it's in between 3.1 and 4.4. Maybe we'll say it's going to be 4. We're not sure with this one yet. And last one's definitely an orange. Maybe we're not sure where that's going to be as well. We said it's an acid. It's definitely orange. Maybe we'll say that's going to be a 4.0 as well. We're not sure. Let's do one more test to really analyze this. So again, that was the methyl orange test. You could predict some values on the pH scale. The last test we're going to do is going to be universal indicator. Last test. Universal indicator. This is the best one, the best test we could do. On a universal indicator, it's like a litmus paper. Show you the universal indicator. Yes. All right, so last test is going to be a universal indicator. This is universal indicator paper, strips. If you're looking at the universal indicator, you notice that it looks like a rainbow kind of. Each color represents a different pH on these strips. So that pink, that fuchsia is going to tell you a pH of 1. That's 2, 3. Orange is like a 3 or 4 or 5. Yellow is like a 6. So all these shades over here are going to be acids. If I rotate this around, those shades, greens, blues, violets, are going to be more like a base. So all units, except my acids were red, bases are blue. This is why. Acids are typically red, bases are typically blue. So this is going to be a more precise measurement for acids and bases. What's in this? pH indicators, universal indicators, they're strips of paper. These have chemicals in there to extract the colors or extract the pHs of the certain levels. I only need 4 strips. So 4 strips of universal indicator paper. And what we're going to do, we're going to figure out what pH it's going to be. This is the best test that we can use. All right, the first one, all I'm going to do, I'm going to take like a quarter of the paper and I'm going to dip it into the solution, the unknown solution. So first one up, dip a quarter of it in or so, in there. Let's see what color it's going to be. So first one up, I dipped it in. You see it change color. And more specifically, it looks like, let's figure out what it's going to be. 8? Maybe 3? Let's get a little closer here. We're going to figure out what that unknown is going to be. We'll match it on up as best as we can. There's a strip. We want to know what the pH is going to be. Any suggestions in class? Anybody? What, Faith? Maybe a 3? See, now we're getting, this is how we get in fights here. We don't know what the pH is. Faith's saying it's 3. Santino's saying it's 2.7. This is where like chemistry fights happen. So you just got to go with whatever you think. So you guys all see things different. I don't care. So I'm going to go with 3. I don't care. 3. Michael wants to get into 2 and 3. In between 2 and 3. Thanks, Michael. So that looks like, I'm just going to say 2.7. I don't care what it is. It's pretty close to 2. It's pretty close to 3. We all see things a little bit different. So I'm going with a pH of 3. Maybe it's something different. But that's still a strong acid, so we definitely figured that out from before. 3 is a pH for the first one. Next one, let's check out that one. Taking my pH indicator, dipping it in. And it looks like a green. Let's match it up. Definitely not an acid. Rotate this around. Before we put the gloves on, here we go. Let's figure out what this one's going to be. 8.5, right? Yeah, it's going to be a little different. Oh, look, these these are past their code. Expired, but we're still using them. All right, so match that up. Someone said 8.5 initially without even looking at it. Match it up. 8.5 is a solid number. It's reacting different now with something else that was there. So 8.5, I'm going with that value. Maybe you see something different. So that's like an 8.5 for the pH. Next up, dipping the pH strip in another unknown solution, and we want to predict what this is going to be. Oof, got dark on this. Match it up again. Match up that strip. See, every time I put the pH paper on this rainbow vial, it contaminates a little bit. So match it on up. Is it a, definitely not 10.835, Santino said. 10.8? Maybe. Maybe you see something different as well. So 10.8, we should know on the pH scale 10.8 is going to be a stronger base. So I don't know where this 4 came from, but it's definitely not 4. It's definitely like a 10.8 maybe. So 10.8 is a solid number for that. And last but not least, unknown number 4. Let's check it out. Put the strip in. That strip didn't change color much. Definitely not on this side of the spectrum here. Zoom in. Let's see what it's going to be. All right, pH strip coming into play. Maybe you think it's 4, maybe you think it's 5.2, maybe you think it's definitely not 6. So this is where you'd work with your partners and say, oh, what color, what number is it? What color is it? Maybe it's 4.5, 5. Are you thinking 5-ish? All right. You know, it's between 4 and 5. I'm going 4.5. 4.5, I'm going with that last set of data. Thank you for playing. So last one looks like it's going to be about a 4.5. Before we said it's going to be a pH of around 4. We weren't really sure. We know it's going to be around 4.5. This is the best test that we could do. So pH is of unknown number 1 is a pH of 3. Tough glare here. There's a pH of unknown number 2 is 8.5. Unknown number 3 is 10.8. And the last one's going to be 4.5. First one up, pH of 3. What is unknown number 1? With a pH of 3, is it water, ammonia, Sprite, or vinegar? What is pH of 3? What do you think there? Vinegar. Vinegar. Unknown number one is going to be the strongest acid. Which one's the strongest acid up here? It's going to be vinegar. Vinegar has roughly a pH of 3. Good. Next up, you know that one's going to be vinegar. We have 8.5. Which one up here is going to be a weak base? Which one's a weak base? So we're done with vinegar. It's not vinegar. Sprite, ammonia, water. Tricky one. Let's skip that one. Let's go to the strongest base. Which one up here is the strongest base? Anybody at home know? Alex, which one's the strongest base up here? Which one's all about the base? Yeah, cool. So the strongest base up here, you would definitely be able to smell it if you waft it up into your nasal passage. It's ammonia. The strongest base up here would be ammonia. So this is going to be 10.8. Unknown number 3 is 10.8. That one's done. Now we're stuck between water and Sprite. Which one's going to have a pH of 8.5? Which one's going to have a pH of 4.5? Is water or Sprite? Which one's going to be water, you think? Yeah. Distilled water would be 7. But typically the water that we drink, the water I bought came out of like an Aldi's bottle, and it's a little bit more basic. Gives you the more of that smooth texture when it goes on down. So the water in this situation was 8.5, a little bit more basic. So this is going to be water, 8.5. And last but not least, the Sprite is more slightly acidic. Got the acid, it has citric acid in the Sprite, which sodas, juices are about 4.5. That's a pH acid-base indicator test. You can predict unknown values by using indicators or universal strips. Anybody have any questions on that demo? Hope you enjoyed it. Again, what do we do in that situation? We took 4 unknown solutions and we determined the pH of the unknowns, and then we figured out what the unknown solutions were from a little key. All right, we analyze examples, we analyze exit pass questions. Now you understand what the lab, the demonstration means as well. So let's take it a step forward. Let's go through and analyze a flick. So back to the home page. Neutralization. So last class we talked about neutralization. We said that neutralization is going to be an acid plus a base yields salt plus water. So let's scan through here, then we'll watch that flick. Here's the unit. We're almost done with the unit. We went through 3 different theories of acids and bases. We went through Arrhenius theory, went through Bronsted-Lowry, we went through Lewis theory. We did the pH scale, we did indicators. Last class, we went through and did some notes on that too. We know Arrhenius theory is going to be acids going to be H plus or hydronium. We know bases are going to be hydroxide, OH negative. We analyze chemical reactions. We analyze common acids, common bases in the reference table. We said Bronsted-Lowry theory, common acids, common bases. Acids are H plus H ion donors or proton donors. Bases are H plus ion acceptors. You know how to identify conjugate acid, conjugate bases too. We know how to figure out pairs. We did that. We looked at some pairs. We looked at Lewis acids and bases. We know that's referring to electrons. We talked about reactivity with metals and acids. Any metal above H2 is going to react with an acid. Anything below is not going to react. We looked at indicators. This class, last class. We spent a whole class going through pH scale. We looked at that a little bit further in detail today. And then last class, we kind of hammered out some neutralization reactions. So topic 5, neutralization reaction. Acid plus a base yields to make salt plus water. That concept right there. We're going to analyze some examples on this topic too. Neutralization reactions. Here we go. Pick something from this video. Get something out of this.
In today's video, we're going to look at the reactions between acids and different kinds of bases, including metal oxides, metal hydroxides, and metal carbonates, all of which. And at the end, we'll see how we can make soluble salts using an insoluble base. Let's start with the metal oxides and hydroxides. Whenever either of these react with an acid, they'll always form a salt plus water. For example, if we combined hydrochloric acid with sodium oxide, which is a metal oxide, the positive sodium ions and negative chloride ions would combine to form sodium chloride, which is the salt, while the hydrogen and oxygen would form water. And if we balanced it, it would look like this. Or if we added sulfuric acid to a metal hydroxide, like potassium hydroxide, each of the negative sulfate ions, which are 2 minus, would combine with 2 of the potassium 1 plus ions to form our salt K2SO4, which is potassium sulfate. And just like before, we'd also get water and then have to balance it. These types of reactions always follow the same pattern. You take the negative ion from the acid and combine it with the positive ion from the base to form a salt, and you always get water. You just have to be careful to get your salt formula right and balance the whole thing correctly. Now, when acids react with metal carbonates, the reaction's pretty similar. They still form a salt and water, but we also get carbon dioxide. So if we took nitric acid and combined it with calcium carbonate, then just like before, we'd take the positive calcium ion from our base and combine it with the negative nitrate ions from the acid. But because the nitrate only has a 1 minus charge, while the calcium's 2 plus, we'd need 2 of them to form calcium nitrate, which would be our salt. And then we'd also get water and carbon dioxide and have to check it's balanced. Now, all of the salts that we've covered so far have been soluble in water, meaning they dissolve. So if we want to make a soluble salt, all we need to do is react an acid with an insoluble base, like a metal oxide, hydroxide, or carbonate. In practice though, to actually carry out this reaction, there are a few different steps that you need to know. First, you place some dilute acid, for example hydrochloric acid, in a beaker, and gently heat it with a Bunsen burner. Then you keep adding insoluble base, for example copper oxide, a little bit at a time. At first, it will keep disappearing as it reacts to form aqueous copper chloride and water. But then as you add more, you'll see that some of the base is no longer disappearing. So at this point, we know that the base must be in excess, and we'll have neutralized all of the acid. The next step is to filter out all of this excess copper oxide using filter paper and a filter funnel, and what we have left should be the dissolved form of our soluble salt, in this case copper chloride. In order to get pure solid crystals of copper chloride though, we'd need to gently heat up our now filtered solution and evaporate off some of the water. To do this, we'd want to use a water bath or an electric heater rather than a Bunsen burner, because we don't want to heat up the solution too much and risk damaging our salt. Once we've evaporated a bit of the water off and we start to see crystals forming, we can stop heating it and leave it to cool, which will cause even more crystals to form. We then filter these crystals out using filter paper and funnel again, and then dry our crystals, either by dabbing them with filter paper or leaving them somewhere warm. And that's it. We've used an insoluble base, plus acid, to make crystals of a soluble salt. So cheers for watching. If you enjoyed it, then please do share it with your friends, and we'll see you next time.
All right, cheers for watching. Thanks for watching that video. All right, moving on forward, here we go. Let's analyze some examples on neutralization reactions. We're on step number 4 for today's class, analyzing examples for neutralization reactions. If you can do these questions on neutralization, you should be able to do the exit pass as well. So we will do this together, and then I'll give you some time in class to work on the exit pass. So please open up the examples, Unit 9, Topic 5A, neutralization. Maybe you want your notes side by side. Maybe you already know this topic. It's easy. It should be an easier topic. I've had students say that this is a relatively easy unit. Yeah, Arrhenius theory questions were easy. Bronsted-Lowry theory questions were relatively easy if you knew the wording on it, what's accepting, what's donating. pH scale should be relatively easy. Indicators wasn't too tricky either. Neutralization should be an easy topic. You're taking an acid, you're taking a base, you're mixing them together, you're blending them together to get something neutral. Real quick before I even go through this topic, let's draw something again. Love my digital drawing here. So if we take a strong acid, so I'm going to take an acid, I'm going to make an Erlenmeyer flask. Erlenmeyer flask has a little neck, and then it has a triangular shape on the bottom. If I take an Erlenmeyer flask and fill it up with some HCl, hydrochloric acid, if this is 1 molar hydrochloric acid, we know the pH of this acid would be roughly 1. So this is HCl solution. It has a pH of 1. HCl, hydrochloric acid with 1 molarity has a pH of 1. That's an acid. We know it's an acid. If I take another Erlenmeyer flask, or I guess we'll take a Florence flask. Why not? A Florence flask is very similar to an Erlenmeyer flask, but it has the, let's try this out, rounded, oh, perfect. Rounded bottom. Erlenmeyer looks like a triangle. Florence or volumetric flask has a rounded bottom. Taking a Florence flask or volumetric flask, I'm taking a liquid here, and I'm going to take some sodium hydroxide. So I'm going to take some sodium hydroxide, which is NaOH negative. That makes it the base. We'll say it's a 1 molarity solution. The pH of this will be pretty close to 14. So this pH is going to be, we'll say 14. I'm going to take both of those flasks and I'm going to add some liquid together into a beaker. So I'm adding it to a big beaker. All right, so you know what's going to happen here. We're going to take something with a pH of 1. We're going to dump it in. So this is going to be added to the beaker. And I'm going to also add the base to the beaker. You mix them both together, you know what's going to happen. They're going to start to neutralize, and whatever's inside this solution is going to have a pH of 7. So the pH of this solution is going to be neutral. You're taking something with a pH of 1, something with a pH of 14. You're mixing them together. It's going to neutralize to pH of 7. Once you mix them together, what else is in here? It's going to form some water. H2O. See that? There's water, H, 2, and O. What else is in here is a salt, which is going to be NaCl. So in that solution, as you neutralize it, you have water and salt, sodium chloride. That's the neutralization process. Acid plus a base yields salt plus water. Here we go. Question number 1. Which word equation represents neutralization reaction? Should be super simple. Neutralization reaction, last thing we wrote in our notes, we said acid plus base yields water plus salt. The order of that could be either way. You could say base plus acid yields salt plus water, or water plus salt. Those could be in opposite orders. Yeah, definitely the best answer for number 1, thank you, Joey, is going to be choice A. 1 is A. Easy one. 1's A. These are Regents questions that you would have seen on the Regents, but you might see them on the ExaPass or the quarter 4 benchmark or the post test. Or you might need it for AP Chem or College Chem. you never know what the road's going to lie ahead. You never know what's going to happen in life. According to Arrhenius theory, a base reacts with an acid to produce. Throw your answer in the chat, please. Best answer for number 2, please throw in the chat. All right, choice D is the best answer. Jordan, we jumped on the bandwagon with you. Everybody in class saw your response, and they agree with you as well. Choice B is the best answer, water and salt. Alex, correct. Thank you very much. Acid plus base yields water plus salt. Easy. Number 3 is a little bit trickier. Let's check this one out. Which equation represents a neutralization reaction? Think of neutralization. Something's neutralized. Think of that process. Something's neutralized. You're taking an acid plus a base yields salt plus water. Neutralization reaction. You're looking for an acid plus a base yields salt plus water. The first thing I would do is I realize it's neutralization. Hopefully you know that neutralization makes a product of water. So you're looking for the product of water. Choice B has a product of water. Choice C has a product of water as well. Water is H2O. It's easy to identify. There's no water in choice A. There's no water in choice D. Can't be A or D. A would represent what kind of reaction? A would be like a decomposition reaction. D would be a double replacement reaction. Compound plus a compound yields a new compound plus another new compound. Now we're stuck between B and C. I found my water. Good. Now we could look for either an acid or a base. Acid plus base. Let's locate, figure out where an acid is, where a base is. Maybe you know hydroxide's a base. Maybe you know hydronium is an acid. Maybe you need to use a reference table. Let's check out the reference table. On the reference table, same page as indicators, I'm scrolling up. There's common acids. Table K, common acids. Let's find an acid here. So common acids, I'm looking at these 4 compounds. I'm trying to locate it on this reference table. H2SO4, there it is. H2SO4, that's an acid. Okay. Hopefully this one in front will be a base. Let's see if this is going to be a base. Scroll down the reference table, common bases. So there's definitely different routes you could take to find this answer. Maybe you know that's hydroxide. There's hydroxide, there's hydroxide. Oh, that is calcium hydroxide. That is definitely going to be a base. Acid plus base yields salt plus water. CaSO4 is going to be a salt. It's an ionic compound. You have a metal. You have a non-metal as well. This is a polyatomic ion on page 2 of the reference table. Best answer for number 3 is going to be choice C. Acid plus base yields salt plus water. 3 best answer is choice C. 3 is C. Let's try number 4 out. Please try out number 4. I'll put 1 minute on the clock. After 1 minute, come up with an answer and put it in the chat, please. So again, please try number 4. Which equation represents neutralization reaction? 1 minute timer. Give it a shot. Thank you. Yes. Good. That's one way to think of it. Thank you. Please record your answer in the chat for number 4. Best response, please. Which one's neutralization reaction? Yeah? Well, we're 4 for 4 right now with responses. Number 4. Did Dexa pass?
I was on titration.
Oh, we can't do titration yet. That's tomorrow's topic.
I was really confused. I was like, what's hydrogen?
Gotcha. Again, this is neutralization reaction examples. Please check that out. 5 for 5. Thank you very much. So 5 for 5. Everybody pick choice C. C is the best answer. Somebody put in the chat that they picked choice C because choice C is the only one that has water as a product. That's one way you can look at this. We know that person knows neutralization is going to be acid plus base yields salt plus water. Found salt in the product, choice C is the only one that has it. If you want to take it a step further, you can say, oh, that's an acid. Base is going to be KOH, potassium hydroxide. The salt in the situation is going to have to be K2SO4. Easy. 4, the best answer is choice C. 4 is C. Next up, number 5. What are the products in the reaction of KOH and HCl? Try this one out. 1 minute on the clock. Please put your answer in the chat once you have the answer. What are the products between KOH and HCl? Please record your answer in the chat. Number 5, best response, please. Thank you. Thanks, Nadina. Thanks, Alex. Thanks, Jordan. Please respond in the chat. Best response for number 5. Maybe we're stuck on this one. I try to help you out a little bit. So here we go. This reaction, we have a couple things. The products are on the right side of the equation. We want to know what these are going to be on the right side of the equation. When KOH, a base, reacts with HCl, acid plus base yields salt plus water. So we should know by now that water is definitely going to be a product. Water is a product, and there should be a salt in there. The salt in the situation, let's use the law of conservation of mass to figure out what's remaining. There's 2 H's on the right. Let's get rid of the 2 H's on the left. There's 1 O on the right. Let's get rid of 1 O on the left. So that's gone. What's the salt remaining? It's going to be KCl. So again, why is it KCl, not ClK? K is going to be a positive ion. It's in group 1. It's losing its 1 electron. Cl is a negative ion. It's always going to be a positive charge followed by a negative charge. There's so much you can do with this. You could name this. This is potassium chloride. You could represent a Lewis dot diagram, K plus, with brackets, with Cl. Charge is -1. You know Cl has 7 valence electrons initially, and then it gains 1 more electron from the positive. All stuff we learned in the year. You can name it. You know it's a binary compound. So it looks like KCl and water are the products. KCl and water. Thanks for responding. Choice B is the best answer for number 5. 5 is B. Next up, number 6. Which equation represents a neutralization reaction? Think about it. Come up with an answer. 1 minute on the clock. You're on the clock. Who the Giants going to get in the draft? Please record your answer once you have an answer. Please respond with your answer in the chat, please. Thank you. Oh, okay. Looks like we're 7 for 7. Thank you for responding. Choice C is the best answer. Why is it choice C? We have an acid, which is HNO3. You can use a reference table to find that. And the base is going to be KOH, definitely. Yields to make water and salt. So this salt is KNO3 this time. How do we get KNO3? Let's get rid of some stuff. Let's get rid of water, which is H2O. There's two H's. Let's get rid of them. H. Let's get rid of the O. O. And let's see what's left. We have KNO3. That's remaining. That is going to be the salt. Best answer for this one right here is going to be choice C. 6 is C. Question 6 is C. Thank you very much. This one, let's check out together. Which acid-base pair will always undergo a reaction that produces a neutral solution? We're trying to neutralize something. So it's either going to be a strong acid and a strong base, or a weak acid and a weak base. So I'm not really a big fan of this because I like two answers here for this one. Choice A is talking about weak acid plus a weak base. Choice B is talking about weak acid and a strong base. pH's levels are going to be quite a bit different there. Strong acid, weak base, they're going to be different there for neutralizing. But the last one, strong acid and a strong base, this would be like a pH of 0 and a pH of 14 would mix together to make a pH of maybe pH of 7. That's a solid choice. A weak acid could be like a pH of maybe 5. A weak base could be like a pH maybe of 9. You mix those two together, you blend them together, that could give you a pH of 7 too. So I'm not really a huge fan of this question. The best response that they were looking for was choice D. Guess second response would be choice A. D is the best answer for this one. Strong acid with a strong base makes a neutral solution. 7 best answer is D. And last question, number 8. 30 seconds on the clock. Given the neutralization reaction, which compound is a salt? Please put the answer in the chat once you derive an answer. All right, thank you for the responses. Please put your answer in the chat for the last question here. Let's see. Thanks, Joey. Joey said C again. Alex says C. Jordan says C. Nadina says C. John says C. All right, a lot of C's rolling in. But we had a problem in class. We don't know what the answer is. We think it's A, B, C, or potentially D. You don't think it's C?
I think it's
Oh, all right. Let's figure out which one's a salt here. So my process of thinking about which one's a salt here. It says neutralization. I automatically think neutralization is going to be an acid plus a base, yields to make salt plus water. Where's the water? Let's get rid of some of these choices. Figure out where the water is. It's funky. It's HOH, but when you put it all together, you combine the like elements, it's going to be H2O. So that's still water, even though the compound isn't organized that way. That's going to be water. That's not a salt. It's water. It's not talking about salty water. That's water. Next up, let's go through some other things. We know acid plus base yields salt plus water. Let's figure out which one's the acid, which one's the base. Let's use a reference table. So pulling out the reference table, I'm going to find and locate my acids, locate my bases. Starting off with the acids, analyze these, figure out which one of the first compounds are acids. Highlighting, going through the process, H2SO4 is an acid. That is an acid. Do the same thing for the base. Scroll on down, find the base. What makes a base? It's the hydroxide. OH, KOH is the base. Oh, we're getting pretty darn close. So we just located, we identified acid, base, and water. So it's definitely not going to be H2SO4. It's definitely not going to be the base of KOH. It's definitely not going to be water, HOH. The salt is going to be an ionic compound, metal, and polyatomic ion, the nonmetal. That is your salt. Choice C is going to be the salt. How can we identify K2SO4? K is potassium. Potassium, if we scroll on down to the reference table, potassium only has one charge. So it's potassium, no Roman numerals. SO4, scroll on through to polyatomic ions. Page 2 of the reference table. Find SO4, polyatomic ions, sulfate. This is potassium sulfate. Potassium sulfate would be the name. Best answer for number 8 is going to be choice C. 8 is C. All right, the examples, you could submit them. You don't have to. I'm not grading them. We're all done with the examples for neutralization. The rest of the class I'm going to give you to work on the exit pass on this topic as well. So I think there's 9 questions on the exit pass. I'm going to close this off. Please go back to the home page. And on our home page, right above, right below examples is the exit pass. So exit pass, Unit 9, Topic 5A, neutralization. Please click on that. Nobody completed it yet. Awesome. So this exit pass is very similar to the examples that we just analyzed on neutralization. Question number 4, just so you guys know, the best answer is going to be A. I didn't mean to put that one on there. 4 is going to be A. If you take 1 mole of HCl, reacting it with 1 mole of NaOH, it neutralizes to make 1 mole of water. That one we were not ready for, but 4 is A. And another one I want to check out quick. This isn't the best acid-base question, but I want to know what, using law of conservation of masses, what is X going to be? So using law of conservation of masses, figure out what's on the left side, figure out what's on the right side, what's missing, what is X going to be? So again, you have from now to the end of class, you have 15 minutes to complete this assessment. If you have any questions, feel free to ask for help. If you don't finish it today, it's going to be due on Saturday. I'm putting you in breakout rooms by yourself. If you have any questions, please feel free to ask for help. I'm here for you guys. Again, please finish up the exit pass from now to the rest of the class. If you're done early, have a great day. We'll see you guys tomorrow. Please join the breakout room. Please complete this exit pass right now. If you have questions, ask for help. Please join the breakout room. Please complete the exit pass right now. Irvin, please join the breakout room. If you need help, ask for help, please.